good morning to everyone. Thank you. We're going to continue this morning session with the second talk, where I will focus mainly on the data and why the data is important. So we call it the power of big data. I'm happy that we already started discussing some of these topics during the first morning session, where the question on data came up, on the importance of this data and what can we do, what steps can we take, and what is the added value of this, and what can we provide to you with the data. So, same formulas in the first session. Just interrupt me at any moment if you have any questions or you didn't understand something. I am completely open to go back and repeat anything that is needed. And I want to be more like an active discussion rather than me just speaking for an hour. Just to have a bit idea of what I will try to cover. So first, this is mainly a rough introduction, but I will focus on two main things. I come from the R&D department. My colleague Vasilis already mentioned that we are very connected to each other. So our job is on a daily basis to support our other teams in the company. One of these is of course SynaptiQ. So we are involved in many research projects, and we try to bring all the state-of-the-art methods, models into our tools, being one of these tools, SynaptiQ, of course. I split it in two main sections. So whatever that is historical and near real-time data, so we call them solar and wind resource data. I will briefly introduce this first, because this is the first that is actually already in SynaptiQ and is used for the calculation of many of the indicators that Vasilis showed us. I do the connection afterwards with the monitoring, so the day-to-day operations and how this is actually used. I touched again some of the things that Vasilis mentioned, like the 3D health scan, and we move towards the more advanced tools like the forecasting that was also briefly introduced, to see how all this data combined together with models can bring added value for you. So, just as an introduction, the word big data is around already for some time. I'd like to summarize it in some few words, but basically the first thing is collecting the data, of course. So we spoke already this morning about different methods of collecting this data, either directly from the inverters, for example, or from data loggers. And thanks to technology today, we can really collect a lot of data. So this is really gigabytes, terabytes of data that comes every day. So the most important is to start organizing this data. We have access to it, that's the first problem solved, but then we need to organize the data in order to take something out of it. So this is the second step, and then the final step is really analyzing and providing added value to it. So this big data can actually help us to take better decisions. So if we are informed, if we have the data, we have the power to take better decisions. We can help, of course, to reduce our costs, so in other words, increase our profit. And we can provide improved products and services. So it does not only allow us to do our daily operations, but it opens also other opportunities for other types of services that are linked to it, like, for example, forecasting, energy trading, and so on. So these are the topics we will cover now. As I said, I will start first what I call historical and near real-time data. So this is really to make just a line between the forecast that is from now to the future and what was before. And I will make the link why this is important and how do we use the historical and near real-time data to do a better forecast of the future. So just as a background, SynaptiQ, as Vasilis mentioned, in SynaptiQ this is fully integrated. So we have access to satellite-derived radiation data. We are trying to cover all the world. We started first in Europe, we expanded to Africa. Recently, at the end of last year, we expanded to America as well. And we are now in the process to go into coverage over the Western Asia, so India mainly. And at some point, we will try to cover the entire world with high accuracy satellite-derived radiation data. You see some details of different satellites we use. So this is also a lot of data that is coming every day to our servers that we need to process. And we need to take the most of it. So this is really high resolution data. We're speaking about 3 kilometers in average square kilometer resolution. And it's historical data that is covering a period for more than 10 years. So this is data from, for example, 2004 all the way up to today, 1 or 2 hours ago. So this is really near real-time data that is being updated as we speak. So this is fully integrated in SynaptiQ and allows the calculation of all the indicators that we saw through Vasilis' presentation. But also, as of last year, we sell this separately. So we started commercializing this and sell it also through our website. So we have a standalone platform where we commercialize this. And we started to provide also direct API access to other customers for them to integrate in their own platforms or needs. But I will focus mainly now on this data and how do we use it actually to take more value. On the wind part, it's the same, so there are different sources. On the wind side, this is a different approach, so it's not really satellite images that are taken over the Earth every 15 minutes. These are reanalysis models, but we use also a combination of different models covering different periods. And thanks to our research projects, we developed models to combine and to take the most and the best of this data to provide the resource. So for example, one of the examples from the wind resource modeling that we do, so taking all this data we do from mesoscale, so large-scale regional mapping, for instance, for resource assessment early stages on a project when it's starting, and we go all the way also to microscale modeling, so we're talking about really 2 kilometers or up to really so few hundred meters. And this really is one of the inputs, for example, that allow us to do better forecasting in the case of wind, and I will show also for the case of solar. Because for wind, I take one step here in advance, but I will come back to it. One of the most tricky parts on wind forecasting is the roughness of the terrain. So this has a really big impact on the forecast model. So we really need to go into a micro scale in order to capture all the effects of the terrain. But I will come back to this later as well. Yes, please.
About the CFSR models that you mentioned, I do know they are the analysis models, but do they provide near real-time forecast as well? They do?
There are some of them that they have a bit of lag, so I try to show it here. Some of them are available up to 3 weeks ago. They call it up to date, but it's not really. So indeed, the satellite part, as I said, this is really 1 hour ago or 2 hours ago. So every 15 minutes we fetch the data from this, and we have satellite solar irradiation data for today. In the case of the wind, it's a bit different. So there is not this availability in time, but some of the models like the CFSR and the CFS, the single version of CFS, are available in near, it's not so near real time, but are improving the model so that we can access this data with more recent records.
I understand that they provide the information about the past, but do these models provide information about the future in order to do the forecast?
No. So at the moment what we do is we take numerical weather prediction models, so this is a different type of modeling. That this part takes the modeling of the future behavior, but in the part of the training the models, we do use research data. So we use historical data in combination with a measurement campaign, for example, wind mass, or what I will cover later is the actual data, the actual production of the wind farms in this case, to combine and correct this historical irradiation data, wind resource data, combine it with the site-specific conditions of the wind farm, and then combine it with the numerical weather prediction models that are really forecasting from now up to 10 days ahead or something like that. So this data, this reanalysis data, is mainly used for, sometimes referred is used for long-term yield assessment, so that's future assessment, but it's really on a more business model case, so it's really to provide a P50 and a P90 estimate of the production of the wind farm. But the real forecasting is done using numerical weather prediction models and training models to account for the site-specific conditions. GFS, yes, SynaptiQ is of course one of the best. DWD, we have regional models as well. I will try to cover that in the next slides indeed. So once we have these models, as I said, we generate time series, and these time series help us to correct the forecasting as a final step, of course. Now, I like also to make the point of why do we need accurate data. So in the past, some few data sources were enough. They were free available sources, and this was okay, this was everything we had. But now we realize, so we have seen by our experience as well, and thanks to the research projects we investigated further, and we know that having accurate data helps a lot. So it really helps us to improve all our models and ultimately our forecasts. So this serves for long-term yield assessments, what I just mentioned before, so it helps us to identify correctly the long-term average expected at the site, and even to spot variations. So I will show some maps on this. To do the performance evaluation during operation. So that is the near real-time data that we use. So the satellite-derived radiation data, for example, that we use to calculate the performance of a plant and monthly reference yield or indicators that Bazefield showed us. And ultimately also to help us to detect faults, to errors. So we can run the health scan that I will show as well to help timely detecting deviations that will impact the production. This The slide shows an example. It's a specific example I choose from irradiation data. So this is a set of hundreds of irradiation devices in the field. Basically, the main message that we wanted to show is that on-site irradiance sensors can have excellent accuracy. It's known that. So the best accuracy that we can get is really with the local sensors. But in reality, as these sensors are in the field, they suffer a lot of effects that if they are not properly maintained, cleaned, installed, and so on, we cannot fully trust in this data. So that is first question mark and an exclamation mark. I said is regular validation of sensors is a necessity. Once we have a dense network of sensors that we can trust, then we can really use this data to improve our calculations, our models, and so on. So I just list some examples here of things that can affect, of course, local sensors, going from soiling, shading, orientation, mismatch, degradation, availability of the sensor or the data logger. This is an example for soil, but of course applies for wind as well. Another example that influences a lot the modeling is the long-term variability. So the renewable energy sources are variable, we all know that. Solar has a strong variability, wind as well. Thanks now to these long-term data sets, we are also aware now of long-term trends. So besides the yearly variability and the short-term variability that we observe, that impacts directly, of course, the cash flow of our assets, there is a long-term variability of the resource that we can quantify thanks to this accurate data. So if we have the accurate data, we can run, this is an example from the Netherlands, where we used really high accuracy data from the KNMI, that is the Dutch Meteorological Institute, to really quantify how much was if there was a trend, and clearly you can see there was a trend. So in the early 70s, the resource seemed to have simply a variability pattern from up to down, from year to year, but suddenly from the 1990s you see that this starts going up. And this impacts directly, of course, the long-term yield assessments. So as part of our research projects, we develop models to take this into account. This is one example model where we do take into account this variability and this trend into the projection of the future. So this is a forecast, but it's not a forecast as I will speak later on. This is really the long-term yield expected energy, but it impacts in our modeling expectations because the resource can continue to increase or can decrease suddenly or can keep on the same level. So all these things we take with statistics into account to improve our modeling. Ultimately, this example shows the effect that can have, for example, if we are on a business case risk assessment, so we are calculating P90s, for example, or P50s, this can have a big impact. So that's why we need accurate data in order to have, as I said at the beginning, informed decisions, to take good decisions and to improve our profit, because we can over or underestimate the risk, and this can have a huge impact in millions of euros in an investment. So the different sensors, I already mentioned, for instance, some examples about pyranometers, so I put it here again, and it's just as an introduction to show a bit further and explain a bit more what do we do and what is our data. So Vasilis already introduced our satellite resource data, and I briefly spoke about it. This table just shows the advantages or the characteristics of the different sensors and why satellite irradiation data is becoming very useful today. Although it has lower accuracy, of course, than a high accurate local sensor, but if used properly and combined, you can get really improved results and added value for the operations. So let me show you a bit more about our solar irradiation data that we have at 3, that again is fully integrated in SynaptiQ, as I said. This helps us to calculate the unambiguous key performance indicators. For example, for your daily operations in SynaptiQ, when you calculate performance ratio or availability, you can have certainty that the calculations, the numbers you're given are coming, of course, with an uncertainty, and you need to know this uncertainty. So we work hard, and often we are developing new validation frameworks to keep up to date the accuracy of our models, and we are transparent communicating to our clients, and I will show you as well some of the results on these validations that we do. So basically the ultimate goal is, of course, to provide functional yield assessments and, as I said, to increase the operation of our assets. So I'm not going to bore you with details, but for example, this just summarizes what type of data that we're using. We're using different satellite products, Meteosat, but also now the American satellites, and we are using older Meteosat satellites that are moving towards the Indian Ocean to try to cover, as I said at the beginning, different regions on the Earth. We use different instruments going to a temporal resolution of 15 minutes, and the main advantage of this is, of course, the availability of the data. So it's always there, and if we can quantify the accuracy of it, the errors of these models, then we can take informed decisions. So as I said, this figure on the right-hand side shows validation, the latest validation result that we published. So we got high accuracy data from meteorological stations. So every single black dot you see on the map is one meteo station coming from Meteo Institute. Recently, just January this year, we added UK, Italy, Spain, Portugal, and we will be happy, of course, of soon adding Greece. This requires, of course, that we can trust on the data that is really properly maintained, properly installed, calibrated, recalibrated, because all the sensors need to be calibrated, because we will use them as reference. So when we know this is the actual measurement, which, by the way, also comes with uncertainty, of course, but once we know that this is the best available, then we can use this to calibrate our models and to characterize the error of the model. So the map shows the error of the satellite. As you see, it's dependent in region. Overall, it's in many cases in Europe, it's in the order of plus minus 2.5%, so that's really good. It's really showing that on an annual basis, so this is the average, the total annual irradiation that's received on each side. So this is really good. It shows that the models have improved significantly from the beginning. In the past, we had many satellite products with models that were not taking physical properties of the clouds, of the atmosphere, of the particles, and so on. I'm not going to go in details there, but what I want to say, and I take it as a message, is that models today have improved a lot, and we can use satellite irradiation data. If we can quantify correctly the errors, then we can take informed decisions and correct our models. On the left-hand side figure, you see it's a bit more statistical plots. The same data that's actually plotted in a map, but it's then split it into the stochastic part of the error on the y-axis and the systematic part of the error. So we can really pinpoint each location, and you can show for any location you have a plant, you can have an idea of the error you can expect. So you can see that, of course, the systematic error is quite small. The stochastic error of